Hi, and welcome back from spring break. Okay, so this is my basement, and this is the board that we're going to try and do our class lectures on. Today we have my assistant Ariana with us to help us, and we're going to be talking about section 10.2, concavity and points of inflection. So what I have written up here is our first example. It says, an investor wants to clean a former industrial property to create a neighborhood park. And then we have this graph here, and this graph is a graph that relates the cost to the money to be spent on cleaning up the property to the purity of the soil. And so some things that I notice about this graph, the first thing that I notice about this graph is that there's this vertical line here at 100% because there's no way that the soil can be more pure than 100%. Okay? The second thing I notice is that the more money that is spent on cleaning the soil, the closer that purity gets to 100%. So the more money spent, the greater the purity. So our first observation is that, well, okay, so let's call this graph something. How about let's call this guy y equals p of x. X is our cost in thousands of dollars, what we're spending to clean up the property, and p of x is the purity. So the observations here are that p of x, our function, is an increasing function. And what that tells us is that our derivative, p prime of x, is positive. So remember, when we talk about derivatives, we're talking about slope. And this graph is always going uphill, so always increasing, slope is always positive. That dog you hear barking, that's Midnight. And she has decided it's time for her walk, but she's going to have to wait. Okay, so looking back on this graph over here, something else I noticed that's going on here. So this graph starts out kind of flat, it gets steep in the middle, and then it starts to flatten out again. Okay. So here at the beginning, the purity, as we read from left to right, the purity is increasing at an increasing rate until we get to a point where right around here, right around 300, bless you, after about 300, the purity is still increasing, but this graph is starting to flatten out. And so we say that the purity is increasing at a decreasing rate. So let me write those things down. So for x values between 0 and 300, our function p of x is increasing at an increasing rate. But for x values that are bigger than 300, so for all of these x values on this top half of the graph where x is bigger than 300, for x bigger than 300, p of x, the purity, is increasing, still going uphill, but at a decreasing rate. In other words, it looks like that purity is slowing down as we read from left to right. Okay. All right. Now, in terms of some business language that's going on here, here we have a couple of things. We have an investment, which is our cost. And so when I think about the cost, I'm thinking of that as our investment. Okay? And what do we get from our investment? We get purity, and so we can think of purity as our return on the investment. Okay. All right, so our return on investment increases as we increase the investment. And take a look at this language over here. Our purity is increasing at an increasing rate. So our return on investment is increasing at an increasing rate. So another way to say increasing rate is to say rate of return. All right, so thinking about that idea, what this graph is saying is that at this steepest point right here, this place right here in the middle, if we increase our investment by just a little bit, our purity is increasing by a lot because our graph is very steep here. So what that says is that our maximum rate of return is going to occur right here at this steep spot. So the maximum rate of return occurs at this point. Okay. So let me write down a few more words about that over here. Our maximum rate of return. The maximum rate of return occurs at x equals 300. So what does that mean? For us, what that means is that for each dollar spent over $300,000, because remember that over here our cost was in thousands of dollars, so when I see the 300 here, that means $300,000. For each dollar spent over $300,000, each dollar will yield less purity per dollar. Another way to say that is that we get our biggest bang for our buck right at this maximum rate of return. Okay? So we get the most purity per dollar invested at this maximum rate of return. Okay? Another piece of language for this is that this point is called the point of diminishing returns. All right, so right at this point, we get our maximum rate of return, and any money spent more than that, each dollar is going to give us, it's still going to increase our purity, but it's not going to increase purity as much as right at this point right here. Okay? Okay, so this is kind of the idea that we're thinking about. Okay, we want to think about where are we going to get the biggest bang for our buck. So we're looking for the steepest place on a graph. And I want to translate this a little bit into just sort of some function notation and some calculus lingo, and then we'll bring it back to this after we talk about it in terms of just generic functions. Okay. So in calculus terms, I'm going to draw a generic function. Here it is. Kind of looks just like the one we just saw, but that's okay. Here it is. Here is our function, and we're just going to call this y equals f of x. Okay. And that point, that steepest point right here, this point right here, in terms of calculus, is called an inflection point. Now, I want to focus on the portion of our graph that's happening before that steepest point, before that inflection point. This portion of our graph, we see that that shape right there is a shape called concave up. Okay. So when I think about a graph that is concave up, I think about any kind of shape that looks like a U shape. And if I were to draw some tangent lines on this U-shaped graph, look at how the graph, we're going to have to stop. We're going to take a time out. We'll be back soon.